let's make a start. Thanks everyone for coming along to this exit seminar for Rhys Williams. I'm sure most of you know Rhys, all of you know Rhys. Rhys was I think a Part 4 student in about 2010, 2011 maybe, and when I offered a project around developing a jet injector in the Level 5 laboratory, which Rhys took up as his Part 4 project, did a fantastic job of it, and we subsequently enticed him to stay on as a PhD student, which he, I think, happily did, although he didn't, by his own admission, really know what he was getting himself into at the time. So Rhys spent, I think in the first year of his PhD, he spent 3 months over at MIT in Boston, working in Ian Hunter's lab, doing some experiments on the jet injection system that he took over with him. Is that right? Did you take something over? Yeah. And working in the bioinstrumentation lab there. And he's been tackling an interesting and important topic that he's going to explain to us about. And I was really pleased to see when he submitted his thesis, which is not yet examined, but not far away, we hope, from being examined, that he made a comment in his acknowledgements section that in reflecting on his PhD project, that he is passionate about this project as he was when he first started, which I was kind of glad to see, but then I kind of thought about it and it implied that could go either way. Just as disinterested now as he was at first, or just as passionate. But I took it the right way, I think, and we're interested to hear what a few years of passion have brought about. So Rhys, the floor's all yours. We look forward to hearing from you.
Cool. So the focus of my PhD was the jet injection of viscous fluids, and I was supervised by Andrew and co-supervised by Paul. So what is jet injection? Well, we load a drug into an ampoule here, and then apply force to a piston, which forces that fluid out a tiny hole at the end of around 200 micrometers, not millimeters, micrometers. That jet then comes out at a speed of up to 200 meters per second. And at that speed, that jet can pierce through the top layer of skin and deliver the drug to the layers underneath, which include the muscle at the bottom, the fat between the muscle and the skin, and the dermis itself. So what's wrong with needles? The major reason to go for a jet injection method rather than a needle and syringe method is the impact of needle stick injuries. Now, over 6% of healthcare workers will be exposed to an infectious disease each year as a result of a needle stick injury. And obviously with jet injection, we can avoid the chance of that happening whatsoever. Also, up to 10% of the population has a fear of needles and injections, and this leads to low levels of compliance with needle delivery, specifically for people who use them a lot, like diabetics. And so moving to a jet injection method will increase the compliance of patients with regular injections. So currently there are commercial jet injectors available on the market using the same process of applying pressure to a fluid and forcing it through a tiny hole. These, however, all rely upon either compressed springs or compressed gas, and as a result of that, do not have any control over the penetration of the jet through the skin and into the layers underneath. And the variability of skin means that having control is a benefit. And that's a benefit that our injectors take advantage of. So we use a linear motor called a Lorentz force actuator, pictured here on the right. This motor is controllable. It performs quieter than the spring and gas jet injectors. It can deliver a precise delivery volume within less than a microliter. It's reversible to allow reloading of a drug, and can perform a two-phase injection. Now, a two-phase injection is when we start with a high-speed first phase of around about 150 meters per second to pierce through that top layer of skin, and then once we've pierced through, back off to 50 meters per second and deliver the rest of the drug at that level. This means that once we've pierced through to a layer, we can distribute the fluid in that layer only, as specific drugs want to be targeted to specific layers. So viscosity, I thought at this point in the presentation I'll give you an idea of the range of fluids that I was working with. So a viscosity level of 1 millipascal second is that of water, which moves fairly freely and we use in everyday life. If you go up to 10 millipascal seconds, it's about the viscosity of antifreeze, which is used in cars. If you go to 100 millipascal seconds, it's similar to olive oil, which resists movement as we move around in like an olive oil bottle. Then finally, if you go to a viscosity of 1,000 millipascal seconds, or 1 pascal second, the viscosity is that of light honey, which is very resistant to movement and stays in form for quite a long time. So the range of fluids I investigated using glycerol is between 1 and 600 millipascal seconds. So what's the motivation of investigating these highly viscous fluids? Well, there are two main drugs that I had in mind when I pursued this project. The first was monoclonal antibodies. These are commonly used for the treatment of autoimmune diseases and some forms of cancer. And about 60% of current research into new drugs is into this kind of drug, a monoclonal antibody. Because of they are proteins which can self-associate, and as a result of the self-association, they develop viscosity, and they can have viscosity of over 100 millipascal seconds. Another type of drug that to keep in mind is organogels. These are highly viscous compounds that are injected into the fat layer underneath the skin and then can sit there and release a drug over a long period of time, reducing the number of injections that people will need. And this is another area of intense research at the moment. So what was my PhD journey? Well, I decided to split it up into 4 main focuses. The first was to develop an electromechanical model of the motor, keeping in mind the viscosity of the fluid in the ampule. The second step was to develop a jet injector which focused on viscous fluid delivery and could deliver a 600 millipascal second fluid at 170 meters per second. Following this, I investigated the causes of viscous loss in the ampule itself using the computational fluid dynamics approach. And then finally, I looked at the dispersion of the fluid in the skin after a jet injection across a range of viscosities. So the electromechanical model, why did we want to model this device and how it behaves? Well, an important part of the motivation was the fact that we only have a displacement transducer on the coil, and there are 2 main elements between the coil and the jet, and that is the piston and the ampule. The compliance of these elements affect the resulting jet speed profile over time at the orifice. So the questions I had in pursuing this model was, first, what is the actual jet speed profile over time at the orifice? What effect does viscosity have on this jet speed profile? And how will the behavior of the injector change if we change certain elements within the design of the injector? And this is the original jet injector I inherited from MIT at the start of my project on the right here. So the first step in my model was an electrical model of what happens within the motor. So we apply a voltage on the left here and then subtract off the back EMF from down here. Oh, I'll use the laser. That gives us the voltage across the coil. I can then use the impulse response function to calculate the current through the coil. And then the force constant at that position will give me the force that's been applied to the mechanics. From there, this force comes in and is applied to the piston. The piston acts like a spring as it compresses during the injection. And then the other end of the piston applies a pressure to the fluid, which also compresses, and the walls of the ampule expand, allowing more fluid to accumulate in the radial direction. A discharge coefficient affects the speed of the fluid that comes out the end of the injector and then the jet emits. And I accounted for all these factors in my electromechanical model. I'm not including the equations to and I'll to not bore you as much, but they are available at the end if you want to ask. In order to look at viscosity, I use what's called a coefficient of discharge. And so this quantified the pressure loss due to the viscosity of the fluid across a range here of 1 millipascal second to 100 millipascal seconds. This is normalized viscosity with respect to water. And you can see that the pressure loss of around about 35% occurs at the higher end of the viscosity range. I fit a log linear model to represent this loss. In order to validate the model, I carried out a piston tip measurement using a high-speed camera, and also a jet speed measurement using a force transducer right in front of the jet as it emitted from the orifice. You can see that it matched well with the piston tip between the modelled and the measured estimate, with the measured and dotted back here. And the jet speed matched well for the period of the oscillations and the steady state jet speed, but the modelled showed a greater level of oscillation during an injection. This could either be because of the response to the force transducer or some compliant elements that I haven't not included within my mechanical model. I then used the electromechanical model to look at how changing different elements within the injector will change the behavior of the device. As we change the spring constant of that piston shaft and increase it, making it stiffer, the overshoot stays the same, but the period of oscillation and the rise time to the first peak decreases. As we increase the friction coefficient, the jet speeds decrease, but the oscillatory behavior stays around about the same. As the bulk modulus of the ampoule is increased, making the ampoule stiffer, the overshoot decreases significantly, and the oscillation behavior reduces. And as viscosity increases, the oscillation stays pretty much the same, while the speeds reduce uniformly. At this point, I pursued creating a stiff ampoule and piston and using that within my system. The stiff ampoule was designed by Brian Ruddy, and I designed the stiff piston. The most important part of the stiff ampoule design is that it has a removable front end that allows us to change the orifice at the end to be a different size using these O'Keefe orifice inserts you can see on the right here. When I changed the parameters in the model to match the stiff elements, I found a good match with the stiff ampoule in the original piston, but then an offset was observed when the stiff piston was used. I believe this is due to the movement of the O-rings as we applied force to the piston. However, the oscillatory behavior matched reasonably well. So the conclusions I made from my modelling was that stiff elements are better as they improve control, matching the jet speed closer to the piston speed, and reduce the oscillations observed in the jet speed. And that a 100 millipascal second viscosity fluid reduced the pressure at the orifice by 30%, causing a decrease in the accordant decrease in jet speed. It also then occurred to me that we could use this in the opposite way, whereby we could use pulse tests with the injector to estimate the viscosity of the fluid in the ampoule if it was unknown. And you can see here that as the viscosity increases from the equivalent of 1 millipascal second to 100 millipascal seconds, you need a greater voltage to achieve a jet speed. And likewise, if you get a lower jet speed, you know that the fluid is a greater viscosity. So here, this is a range of fluids that I was not aware of the viscosity of when I tested them. I used the injector to estimate the viscosity, and then on the right, I tried to achieve a range of jet velocities with an unknown fluid of 12 millipascal seconds measured viscosity, and achieved good results for the achieved jet velocity. At this point, I moved towards trying to create a viscous fluid jet injector that could achieve high speeds with high viscosity fluids. We bought a commercial BEI motor, which is here on the left, and then attached that to a system that could apply the force to the stiff ampoule and stiff piston. Linear potentiometer was again used to measure the position of the coil. This device was able to apply force of up to 400 newtons, had an adjustable orifice diameter, used the stiff elements that I've talked about, and performed consistently as the voltage was applied. Use this control system here with a National Instruments compact radio system with a onboard controller, an FPGA chassis, and then C-series modules to do the inputs and the outputs. And then these big AE Tecron amplifiers, which are around about the size that they are on that screen, to amplify the voltage up and apply it to the injector. If you look at the comparison between the original jet injector and the new viscous fluid jet injector, you can see that the original performed better with low viscosity fluids, but the viscous fluid jet injector performed better with high viscosity fluid, as you would hope. I analysed the energy within the viscous fluid jet injector, and here you can see that in comparison to the applied energy at a peak of 35 millijoules, we get a jet energy of around about 3 millijoules peak, which shows the efficiency of the system. This was slightly better than the original jet injector system. And then I wondered what would happen if we changed this orifice diameter across a range of viscous fluids. With water, the jet speeds achieved across the range of orifice diameters was pretty much the same. However, once you increase the viscosity of the fluid to 600 millipascal seconds, the jet speeds started reducing at low steady state forces, showing the effect of this viscous loss on the jet speed that comes out the ampoule. The discharge coefficient here is the jet speed over the expected Bernoulli jet speed given it, which is the jet speed that, if there was no viscous loss, would be achieved. So it's like a normalized measure of the amount of the speed of the injector, of the fluid, sorry. So now that I had established this kind of viscous loss, I then wanted to investigate that with a computational fluid dynamics approach. The geometry I took from the original inject ampoule, around about 2 or 3 millimeters from the end of the ampoule, and the axisymmetric representation of that is shown here on the right. There were 2 areas of mesh refinement to improve the performance of the model, and I applied an inlet boundary condition here and an outlet boundary condition at the orifice. The model implementation showed consistent results across different meshes with a less than 0.5 meters per second difference in jet speed with a degree of magnitude in the number of elements in the mesh. It also showed that the model was consistent as I changed the linear turbulence from 1% to 10%, indicating that this setting did not affect the results of the model. Here on the left we can see the jet speed profiles for a range of different viscous fluids. Water exhibits a jet speed profile similar to plug flow, whereby it only reduces down from the Bernoulli jet speed near the walls. However, the 600 millipascal second fluid exhibits like a laminar speed profile in the middle, but has steep slopes at the edge. A comparison of these jet speeds with the experimental jet speeds shows a good match up until 100 millipascal seconds, and then a overestimation of viscous loss in the model for a 600 millipascal second fluid. This mismatch led me to pursue changing different parameters within the CFD model to try and see if I could find the cause of the mismatch. Now, within the model was temperature-dependent viscosity of glycerol, whereby when you, as the glycerol was exposed, formed viscous heating near the walls as it was forced through the orifice, it would heat up and then reduce in viscosity. When I removed this, it performed worse. So this showed that this is an important part of how viscous drugs are delivered with jet injectors. A range of other simulations showed no improvement apart from an increase in the outside temperature to 30 degrees Celsius and an increase in the roughness simulated within the model. A planar model matched well with the experimental, but is more akin to simulating two parallel plates than the ampoule itself. The model gave us some results, as some insight as to what was going on inside the ampoule. This is the center of the flow, and then here you can see the wall and the orifice on the right-hand side. With water, the turbulence is developed along this wall, and this causes the decrease in jet speed near the wall. However, with viscosity, with the 600 millipascal second fluid, this turbulence does not develop to anywhere near the same degree. For both fluids, the pressure profile with the inject ampoule was very smooth and decreased down to 0 at the outlet. Here you can see the extent of that viscous heating with glycerol. Near the wall, you're seeing an increase in temperature of over 60 degrees Celsius. I then moved on to simulating the stiff ampoule. Here you can see a micro 2T reconstruction of the stiff ampoule near the orifice, and then this is my representation of it with an ANSYS, showing the same boundary conditions and similar areas of refinement. Here the jet speed profiles were similar for the 635 millipascal second fluid, but showed the secondary slope near the walls for low viscosity fluids. I will be investigating that on the next slide. On the right here, we have the match with the experimental results. And once again, you can see that it doesn't perform as well at high viscosities, with the drop-off occurring again near this 100 millipascal second level. If we look at the turbulence with water, you can see that there's much greater magnitude and breadth than was observed within the inject ampoule, which explains the slope that we see near the wall here. The pressure profiles on the right show that the pressure is much less smooth than experienced in the inject ampoule and actually drops below the cavitation limit, indicating that there could be bubbles forming right at the sharp edge here, which will affect the flow. I could also look at the shear rate of the experienced by the fluid within the ampoule, and a shear rate of above 10 to the 7 has been shown to cause damage to monoclonal antibodies. However, even though this occurs within these profiles, only around about 5 to 10% of the fluid is exposed to that shear, with most of the fluid being exposed to levels beneath the threshold. This matches with experimental results presented by Kathy Hogan. So my conclusions from the CFD work was that the viscous loss develops along the smooth long walls of the original ampoule, and that viscous heat plays a very important role in allowing high viscosity fluids to achieve higher jet speeds. I also found that the sharp corner of the geometry of the stiff ampoule is likely to cause cavitation, and this is an area of future work. The final question I wanted to answer in my PhD was where does the fluid go after we inject it across a range of different viscosities, and is viscosity a factor in the dispersion pattern of the fluid if the jet speed it's being delivered at is exactly the same. A previous paper had shown that if you change the viscosity of the fluid, it would change the pattern, but they did not account for the effect on the jet speed that the viscosity would have. And so firstly, I did some preliminary tests into gels, measuring these factors shown here. And the p-values for the influence of viscosity suggested that only area was affected as viscosity increased, with a decrease in the dispersion area in gels. These gels are polyacrylamide gels, commonly used as skin models within the jet injection literature, but they break into a plane once you inject, and only an estimation of the dispersion expected in actual skin. So therefore I moved on to tests in pig skin itself. Here you can see the three main layers that we are concerned about: the dermis, which is the skin, the fat, and the muscle. And in order to simplify the analysis of the results, I extracted two main measures, one of the XY distribution and one of the depth in Z. Here you can see what we can do with micro-CT, whereby the surface of the skin is visible by the excess fluid on the top, and then the fat is visible by the holes that are formed due to the presence of adipocytes. This micro-CT method allows us to analyze the distribution in a way that just cutting through the skin wouldn't allow us to do. So I'm going to focus on the effect on X-ray distribution, as this showed the greatest difference between viscosities. This plot, any overlap with 0 shows that the comparison is not significantly different. And this overlap with 0 occurs for every single comparison of every fluid that I injected, which shows that viscosity has very little effect on the dispersion in the XY plane. The results were similar for both the depth of the fluid and the dispersion pattern, and the percentage of the fluid that was delivered through the surface of the skin. We had an interesting range of patterns during my test. You can see here on the left that there is a thin jet of fluid that has passed through the dermis, gone through the subcutaneous fat, and then some fluid is left seeping into the muscle at the bottom here. Here most of the fluid is distributed within a subcutaneous fat layer, and then here some is distributed in the dermis, and then some is distributed in the fat. And you can see the interface of the fat and the muscle along this here, forming a kind of arrow, indicating how that interface sat as the injector pushed down upon it. This really highlighted the importance of how these interfaces control the dispersion of the fluid once it's been injected. My conclusions from my dispersion tests were that there is no significant effect of viscosity if the jet speed is kept constant across different viscous fluids. I also identified that skin variability between injections and between samples is a major factor in the formation of the dispersion pattern, and more investigations need to be done in order to determine how we can use information about skin properties to control the dispersion of the jet. Again, we want to get it into the right layer so that it behaves better. At this point, I've reached the end of my journey, as I had covered the impact of viscous fluids on the electromechanical behavior of the motor. I developed a jet injector for viscous fluids. I looked at the viscous loss in the ampoule, which is the primary impact of viscosity on the delivery of viscous drugs, and looked at the dispersion of viscous fluids in skin. In conclusion, I had created an electromechanical model. I had identified a 30% decrease in pressure due to the viscosity of 100 millipascal second fluid. I built a jet injector capable of forming 170 meters per second jet of a 600 millipascal second viscosity fluid, which had not been done before. I determined that a 200 micrometer orifice diameter is best across the range of viscosities that I investigated. I had found that the temperature-dependent viscosity plays a very important role in the formation of the jet in the ampoule, allowing high viscosity fluids to reach higher speeds. I identified the influence of the ampoule walls and the influence of turbulence as the causes of the pressure loss in the ampoule across the range of fluids. I showed that if viscous loss is accounted for, viscosity has a negligible effect on drug dispersion in skin in comparison to the variability between skin samples. So for future work, I would recommend firstly pursuing a cavitation model to look at to improve the performance of the stiff ampules CFD model. I would also like to look at the computational fluid dynamics of more geometries to gain a broader picture of what is causing viscous loss within the ampule and verify some of my assertions. I'd also like to do further investigation into the mismatch with the 600 millipascal second viscosity fluid and try and figure out a way to model that better within the CFD environment. We should also pursue the identification of skin properties that influence drug dispersion, as more information about these skin properties will allow us to control the dispersion of the drug better. And currently we are pursuing a reduction in the size of both the motor and the electronics associated with the injector, allowing injectors, our electronically controllable jet injectors, to be more portable and more useful in a clinical environment. And we should also pursue the injection of actual monoclonal antibodies in organogels, looking maybe at the effect of the shear on their performance, and also just to verify that they perform as expected based upon my results. I'd like to acknowledge the contributions from my two supervisors, Dr. Brian Ruddy, who helped me a lot in the last couple of years of my PhD. My advisory committee, which included both Kathy and Ian at MIT and Richard and David here at the ABI. Peter Blythe and Stephen Olding, who were the workshop managers during my time here. John Cater and Stephen Waite, who helped a lot with the CFD work in the end of my PhD. The Biolab in general for everything. And the ABI in general for being such a great place to work and for having all the resources that we need to do some really good research. My friends and family for all their support, and the funding from Portal Instruments, the Vice Chancellor's Strategic Development Fund, and I was supported by a doctoral scholarship. Yeah, I'll leave it open to questions.
Okay, Reese has left himself plenty of time for questions, so happy to take any from the floor.
With the stiff injector, with the replaceable nozzle, there was a lip that caused many problems, the cavitation. And in the conclusions you said that an area that you'd like to pursue, or you think the jet injector group should pursue, is getting a better model of cavitation. Is that sensible? Would it be better not to investigate how these nozzles could be made more better by making them smoother?
Well, we have characterised that that if it is smooth, it won't be likely to cause cavitation. But given the performance of the jet injector that did have that sharp edge, it would lead me to want to investigate why that increased performance is related to this sharp edge. I don't know whether that sharp edge is actually improving its performance with viscous fluids, either through allowing it to have a steeper gradient on velocity near the wall. And so that's why I consider it an important area going forward. Yeah.
Martin?
So this might be, and thanks for a great talk, this might be a future worky thing, but I guess if I were to predict the performance of such a device on actual skin, I would have sort of predicted that the interfaces between the different layers is a potential weak point, in the sense that that's where stuff is likely to go. And I think on the very first slide that you put up, you showed something about dye staining, I think it was, and you showed that the peaks in those stains were indeed in those interfaces, and yet the slides that you showed after that, it was inconclusive as to where those interfaces were. So is that consistent through the experiments that you found? Was it the layer between the dermis and the fat, or the interface between dermis and fat, and the interface between fat and muscle? Is that where everything ended up with your skin experiments, or not?
So during my skin dispersion experiments, I was aiming to get into the fat, and I didn't change the jet speed between each experiment. So the dispersions were generally centered within the fat. Normally at that interface, or like the bottom of it will sit at the interface between the muscle and the fat. And I tried to be consistent in how I chose samples so that they had similar depths of the dermis, the fat, and the muscle in order to try and reduce that effect.
The fat layer, is that where these things need to go?
Well, for hormones, you want to get it into the fat, and also for some monoclonal antibodies. The contrast fluid shows up best in the fat region of the skin. So targeting that area allowed me to see the dispersion pattern more easily, I guess. Yeah.
Would there be any advantages in controlling the temperature of the wall of the ampoule in terms of viscosity of fluids and injection?
Yeah, so I imagine that if you could raise the temperature of the wall without hurting the patient while you're delivering it, then you would be able to achieve high jet speeds with viscous fluids as a result, as long as it exhibits reduced viscosity at high temperature. Yeah.
And doesn't get damaged in the process, right?
Yes, yeah, sorry, yeah.
Yeah, so that was what I was thinking about. So if your treatment temperatures of 80 to 100 degrees, is that likely to degrade the drug?
Yes, so in that wall region you have the effect of both the high temperature and also the high shear, which is causing the drug to denature and then be ineffective. But because it's near the wall and is only over a small area of that profile, it's only around about 5 to 10% of the drug that's been exposed to that, with most of the drug passing through without experiencing both of those factors. Yeah.
This seems like a really great idea, but I'm wondering why, is there not general uptake of the jet injectors? There are other products on the market, but presumably they've been around for a few years, have they? So what's really holding everything back?
For the commercial jet injectors?
Yeah. You mentioned, you clearly identified the need to explore the ability to target the viscous fluid into the right area. But is there something, is that the number one thing that's holding it all back?
So for commercial jet injectors, they have been shown to cause similar pain to a needle and syringe injection. So that might be one of the factors in their lack of uptake. But also because of the lack of control, they're quite inconsistent in their delivery. And we hope that with our use of a controllable jet injector that we can gain consistency that they don't have.
So this will help to solve the uptake problem.
Yeah, hopefully.
Are they expensive to make? The one that you built, would that be a major problem with the hospital administrator to buy? So while compared to a needle and syringe, they're more expensive. So if you're looking at about $150, but the administration costs, including the need to treat people who are exposed to anesthetic injury and the disposal of sharps that is required with using needles, means that overall the jet injection method ends up cheaper because the costs associated with those things are high. I was also thinking if you get this really under control and you wouldn't need a nurse to do it, you could probably do it yourself.
Yes, yeah, that's true. Especially if you have a kind of interface between you and the device, which is intuitive. Yeah.
Are you thinking